Hello everyone and welcome to the Scalable Predictive Analytics with H2O course. My name is Marion Kipsang and I will be your instructor today. So on to today's agenda. We have 5 minutes for learning outcomes, 15 minutes for what and why, another 15 minutes for reading and quiz, 60 minutes for practice, and then the next steps, what to do after finishing the course. So on to our learning outcomes. By the end of this course, you are required to be able to describe the syntax and parameters of common algorithms in H2O and also to know these common algorithms. You should also be able to illustrate how H2O handles data preprocessing and feature engineering tasks. You should be able to apply various machine learning algorithms from the H2O library to solve real-world problems. You should be able to evaluate the performance of your machine learning models. So how well does it perform when given real-world data? And you should also use appropriate metrics for measuring this performance. You should also be able to assess the generalizability and robustness of your model across different data sets. Now, what is H2O? First of all, H2O is an open source software used in data analysis for machine learning and artificial intelligence capabilities. It also provides a platform for building advanced analytical models in data science and machine learning. It also supports a wide variety of statistical machine learning algorithms, making it very versatile to use in classification, regression, clustering, and even anomaly detection. Some real-world examples of where we can use H2O, we have that you can use it in e-commerce. Companies that deal with e-commerce can utilize H2O to build predictive models and to identify customers at risk of churn. So by analyzing customer behavior, such as purchase history, browsing patterns, and engagement metrics, H2O helps businesses take proactive measures to retain customers. Other than the e-commerce industry, there are many other industries where H2O can be of use. For instance, modeling risk in financial settings, and even drug discoveries by pharmaceutical companies. Now, on to why H2O is important. H2O is important in very many different ways. First of all, it being open source means it's freely available to the public. So you can take a look at the code and you can also modify it as an individual. H2O has also been designed to operate in distributed computing environments. This allows users to scale their machine learning tasks across multiple machines. So this makes it very easy, especially when working with very large data sets. You will leverage the power of distributed computing environments so that you can do your analysis a lot faster than if you were using just one computer. And then it also supports a wide range of machine learning algorithms. This enables users to choose the most appropriate algorithm for their specific project. And another feature that H2O has is AutoML, which in full stands for Automated Machine Learning. This automates the process of machine learning model building process by performing model selection and hyperparameter tuning to give you the best performing model out of the available models within H2O. H2O also provides features for model interpretation and visualization. This helps users understand how machine learning models make predictions. So you can look at for regression, you can be able to access the metrics, for instance, the mean squared error. And for classification, you are able to look at log loss, accuracy, and other appropriate metrics for evaluation. H2O also provides APIs and interfaces for various programming languages. For instance, H2O supports R, Python, and Java. So moving on to the features of H2O. H2O has been designed to work in a distributed computing environment. So this leverages the power of parallel processing and scalability across multiple machines. So if you have a very large data set, it makes it easy to analyze your data quickly and efficiently. It also includes a wide range of machine learning algorithms. For instance, it has the distributed random forest algorithm. It has the generalized linear model algorithm, among many others. As we had said earlier, H2O also has AutoML functionality. So this automates the process of training and tuning your machine learning models, giving you the best performer. H2O also provides APIs and interfaces for popular programming language. As we had said, H2O supports R, Python, and Java. H2O also includes features for model interpretation and visualization, allowing users to understand and explain the decisions made by the machine learning models. This also enables us to interpret, this gives us metrics for interpretation for the different models. Now, let us compare H2O with other machine learning libraries. So when it comes to ease of use, we will compare H2O with scikit-learn and TensorFlow, which are other popular machine learning libraries. So on ease of use, H2O provides a user-friendly interface and high-level APIs. Scikit-learn, on the other hand, is beginner-friendly and has a well-documented API. TensorFlow has a bit of a steep learning curve and is best used for complex tasks. And then when it comes to distributed computing, H2O has been designed to work in distributed computing environments. Scikit-learn has no support for distributed computing environments, but TensorFlow also has support for distributed computing environments. When we come to the AutoML capability, automated machine learning, H2O has a built-in automated machine learning process for model automation. So what it does is it performs model selection and hyperparameter tuning, giving you a list of the best performing models. Scikit-learn has no automated machine learning capabilities, and TensorFlow has no support for automated machine learning. So for TensorFlow and scikit-learn, you are required to manually tune your models. There is no automated tuning through the use of AutoML. When it comes to interpretability, H2O provides model interpretation features. And actually, once you've trained your model, you can print out some information about how your model has performed and how well and what measures it has taken while training the model. Scikit-learn has limited interpretability tools when compared to H2O, and also TensorFlow has limited interpretability for deep learning as compared to H2O. Moving on to integration with other languages, H2O is integrated with R, Python, and Java. Scikit-learn can only be used with Python, and TensorFlow can be used with Python, C++, Java, and Go. On to scalability. H2O is designed specifically for scalability as it supports a distributed computing environment. Scikit-learn is only suitable for small to medium-sized data sets because it has no support for distributed computing. TensorFlow, on the other hand, scales well for deep learning on GPUs. Then use cases. H2O is widely used in various industries for predictive modeling, anomaly detection, among other artificial intelligence tasks. On the other hand, scikit-learn is a general purpose machine learning language, general purpose machine learning library, and TensorFlow is primarily used for deep learning applications. Now, some related tools when working with H2O, you have Python and R, which are the main programming languages that have been supported by H2O. You have Jupyter Notebooks, which is a platform that supports collaborative development among different users. We have Apache Spark, which is used for distributed computing. We have scikit-learn. We can also use scikit-learn alongside H2O. And then we have data visualization tools like Matplotlib and Seaborn, and database systems and cloud platforms like AWS, Azure, and Google Cloud. Now, important H2O concepts. Some important concepts include distributed computing. So H2O has been developed specifically to scale across a distributed computing system. So this means that if we have very large data sets, we can make use of parallel computing so that our analysis can be carried out much faster than it would have in a single computer. And then it has machine learning algorithms. There are different types of machine learning algorithms under H2O. So H2O provides machine learning algorithms such as a distributed random forest algorithm, deep learning algorithm, generalized linear model algorithms, among others. H2O also has model interpretability. When we are able to, H2O provides performance metrics for our models, so we are able to interpret how well our model is performing when exposed to real-life data sets. And then we have scalability and performance. So H2O can be scaled into distributed computing environment, thus improving its performance and saving on time, especially when working with very large data sets. Now, for 10 minutes, you will be able to access the reading and quiz resources. So the reading resources just have a bit more information on H2O and its advantages, its limitations, some steps for implementations and references. And then within that 10 minutes, you also have a section for quiz. This for the quiz, you will answer these questions and then you will be able to evaluate how well you have understood the reading material. Now, after reading and quiz session, we move on to the practice session. So in the practice session, you'll be given, we will go through a workshop notebook that has some code on how to implement or perform machine learning tasks using H2O. And then after we are done with the practice session, the next steps is to complete the project. So you'll be given a project and a guiding notebook that will sort of guide you as you go through implementing machine learning models to solve real-world problems. And then you will submit your notebook for evaluation. Now onto the practice section. So to be able to run the code on your own machine, go to File, Save a Copy in Drive. So that is File, Save a Copy in Drive, and then you connect it to, so File, Save a Copy in Drive, and then connect. That way you will be able to run the code in your own machine. So we will start by importing the necessary libraries. We install the H2O library and then we import it. We will also import matplotlib for visualizations, and we will import numpy, which we will use to deal with arrays. And then we initialize our H2O. So as you can see, it is downloading H2O. And from the information here, you will see that it has also set up a cluster. As we had said, H2O is can be used in distributed computing environments. So now, as we have imported it and initialized it, it will set up a cluster where it will carry out the data analysis, the analysis that we require it to carry out. As you can see, it has created a cluster. Here we have some information about the cluster. So uptime is 4 seconds, time zone, data passing time zone, cluster version. So all these things indicate that our H2O has initialized correctly. Now we will move on to regression. When we perform regression, we're interested in predicting a continuous variable. So what we will do first is we will load our data set. So here we will use housing data set. This is data from a 1990 census on housing prices in Boston. So the data set, we can preview the data set. We will load the data set from using H2O from this website, and then we will explore the data by looking at the first 10 entries in our data set. So as you can see, this data has longitude, latitude, house median age, total rooms, total bedrooms, population, households, median income, median house value, and ocean proximity. So yeah, sorry, it wasn't the Boston data set. This is the California housing data set. So our target variable is the median house value. And that is the variable we are interested in predicting. So first of all, we will specify which columns are the predictors, or which columns are the features, which columns are the features and which columns are the outcomes. So the response and predictor columns. So we set the response column to be the median house value. This is the column which we want to predict. And we set the predictors by removing the response column. Now we will split our data into a training and testing set. So here we take our data, reg_data, and we use the split_frame function. And ratios is where we set how much of our data we will use for training and how much will be used for testing. So giving it 0.8 ensures that our training data will be 80% of the data set, and our testing data will be 20% of our data set. And we include seed so that however many times we run this code, we get the same outcomes. So this seed is just an arbitrary number, but setting it ensures that every time the data set is split for testing and training, we will have the same outcome. Now, moving on to modeling, our data is now ready to be modeled. So we will start by using the gradient boosting machine. So a gradient boosting machine, it effectively combines the predictions of multiple weak learners to create a strong learner that is capable of making accurate predictions. So here we will import our gradient boosting estimator. Oh, and one thing about H2O models, the models are generalized. So the models, any model can be used for regression and can also be used for classification. So we start by importing the H2O gradient boosting estimator. We define the model, we call it GBM_model, which is an instance of the gradient boosting estimator. And then we train it by giving it X as our predictors and Y as our response column, and the training frame as the training data set that we had split earlier. And then after this, we can print the outcome of our gradient boosting machine. So as you can see, it has given us a lot of information here. So it has told us that this model consists of the number of trees in this model are 50. And the most important predictor variable, as you can see down here, is median income, followed by ocean proximity and then longitude and latitude. What we also have here is the scoring history. The scoring history gives us insights to how the model performance has improved with the addition of more trees during training. So we have number of trees and root mean squared error here. So as you can see, with the increase in number of trees, we have a decrease in the root mean squared error. And then overall, we can conclude that the trained model appears to be a promising candidate to making predictions on unseen data. Now let's make predictions on unseen data. We will use the model and the predict function, and to it we give the testing set. So and then we can evaluate the model performance. So to evaluate the model performance, we use the function model_performance, and we apply it to the model, giving it our testing data set. Then we can print out the performance of our model. So as you can see, we've been given mean squared error, root mean squared error, MAE, RMSLE, and the mean residual deviance. So the model evaluation metrics on the test data are consistent with those reported in the training data. So this shows that our model performance generalizes well to new and unseen data. And then the RMSE of approximately 53,665.36, it indicates that on average, the predicting house prices deviate from the two prices, the true prices, by around 53,000, which is not very bad. The MAE, this indicates the absolute difference between the predicted and actual housing prices to be around 36,878. And the RMSLE, it suggests that the model performance is relatively good considering the scale of the target variable. So overall, this model appears to provide reasonable predictions, and its performance is consistent with what we had seen in the training phase. Now, to improve the performance of our model, we can choose to perform hyperparameter tuning. So parameters are the rules which the model learns when the relationship the model learns between the features and the output. On the other hand, hyperparameters are the configurations of the model. So for instance, if you think about a linear model, your parameters are the equation of the line, maybe the equation of the regression line, but our hyperparameters are the configurations of our model. So here we can set up hyperparameters. We can say for number of trees, we will try 50, 100, and 150. And then for the maximum depth of the trees, we can have 3, 5, and 7. And for the learning rate, we can have 0.1, 0.01, and 0.001. Now, let me explain as I run this cell. We define our grid. So by using grid search and giving it our model and our set of hyperparameters, we then train the models. We say grid.train. We give it the predictor variables, the response variable, and the training frame, which is the training data set. And then we obtain the best model, which is we select the first on the list of, so the models are listed by performance. So we pick the first one, which is at position 0, and then we can print out the best parameters. So as we can see, we have been able to get the best parameters from the model. Now, what we're interested in is, has hyperparameter tuning improved the performance of our model? So by that, we can get the best performance. We take the best model, and to it we apply, we use the function model performance, giving the function our testing set. Then we can print our model performance. As we can see, if you compare this to the outcomes up here, you can see that the root mean squared error has dropped from 53,665 to 44,727. So we have been able to lower the errors, which means that the hyperparameter tuning has worked and has actually improved the performance of our model. Now we will move to the generalized linear model. So this is a flexible and widely used model that extends the traditional linear regression model to handle a broader range of data distributions and response types. So same as the previous model, we create an instance of our model, train it, giving it the predictor variable, the response variables, and the training set. And then we can print the model performance. We can print information about the model and see how it has performed. So here we can see that we have used a Gaussian linear model, and we have also been able to see that the most important variables are median income, followed by ocean proximity, followed by latitude and total rooms. And we can see that we have a root mean squared error of 114,503. So we can look at the performance of this model. So we make predictions using the model, using the predict function and giving it the testing set, and then we can print the performance of the model. So here we have a root mean squared error of 114,000, which is consistent with what we had seen on the training frame. So we had seen in training, we have a root mean squared error of 114,503. And when testing it, we have a root mean squared error of 114,635. So they're consistent. But as you can see, this performance is worse than what we had earlier with the gradient boosting machine. So we can try and it by performing hyperparameter tuning. So we will define our set of hyperparameters, define our grid, and then train our models using cross-validation. And then we get our best model and we print the best model parameters. Now, as we can see, we have a list of the best model parameters, but what you're interested in is, have we been able to improve performance? So as you remember earlier, we had a root mean squared error of 114,635, and now our root mean squared error is 84,430. So we have been able to improve the model's performance, although it is not performing as well as the gradient boosting machine. Now you can carry out this challenge. We have a challenge where you will be required to use this data set. This is a data on Boston housing. So it is still, it is a data on Boston housing, and what you're required is to implement a H2O deep learning estimator and make predictions and evaluate its performance. Apart from that, you can also choose to improve its performance by tuning hyperparameters. Now, moving on to regression using AutoML. As we had said earlier, AutoML is automated machine learning. So this feature, what it does is that it trains different models and then looks at their performance and then ranks them according to their performance. So what we do is we first import H2O AutoML, and then we define the AutoML model. We give it maximum runtime in seconds, being 600 seconds. We give it a stopping metric. Since we are doing regression, our stopping metric will be RMSE, root mean squared error, and we'll give it a name, let's say regression example. After that, we train our AutoML model. So we train it by using the train function, giving it the set of predictors, the set of response column, and the training data set. And then we can view the leaderboard and see how the models have performed and which one has performed better than the others. This will take a long time to run, so you can pause the video as it runs. So as we can see, AutoML has finished training the models, and we see that our best model is a stacked combo, all models 3, AutoML 1. Yeah, so this first one is the best model, and as you can see, its root mean squared error is the lowest, which is 45,133. So this table provides the performance metrics for each of these models generated by AutoML, and the models are sorted based on their root mean squared error values. So the best performer here has the lowest root mean squared value, root mean squared error value. And the stacked ensemble models, as you can see, are generally having lower RMSE values compared to individual models like gradient boosting machines. Now we'll get our best model from AutoML, and on that best model, we'll use it to make predictions on the testing data sets, and then we can obtain its performance and we can look at its performance. So as you can see, its performance on new data is even way better than the gradient boosting machine that we had seen earlier. Its RMSE is 44,378, while that of our gradient boosting machine after hyperparameter tuning was still at 55,000. Yeah, it was at 45,000. So here we've been able to lower it to 44,000. Now moving on to classification. Here when we talk about classification, classification involves predicting a discrete variable. So we will start by loading our data set. So this data set is a data set of breast cancer tumors. So we can load the data set using H2O and preview the data set and see what kind of data we have. So here we have the ID, the diagnosis, the radius mean. The diagnosis column is our response column. So we want to predict whether a tumor is malignant or benign. So we have M for malignant and B for benign. So as you can see, we also have other features of the tumors, such as radius mean, texture mean, perimeter mean, area mean, smoothness, compactness, concavity, concave points, symmetry, fractal dimension, all these other features. So they're features of our tumor, and they will help us determine whether a tumor is benign or malignant. So first of all, we will specify the response and predictor columns. So our response column is diagnosis, and we will convert it into categorical by using the as factor function. And then we also define our predictor variables. We split the data into a training and testing set, and then we can begin to model. Now we will first use a random forest estimator. So a random forest estimator is a powerful and scalable algorithm that can handle large data set and high value feature spaces. Just the same as regression, we import our model, H2O random forest estimator. We create an instance of the model. We train the model with our predictor variables, our response column, and our training set. And then we can print information about the model. As you can see, it has a lot of information. We see that our random forest estimator has 50 trees. We can also see the mean squared error, root mean squared error. But what we're really concerned with here is the confusion matrix. So if you look at this confusion matrix, we can see that the accuracy, the model has been able to predict very many instances correctly, indicated by the leading diagonal of this matrix. So 276 benign and 158 malignant tumors have been predicted correctly. So we can also look at this table, and we look at accuracy. So the highest accuracy achieved was 0.964444, which is a really high and really good accuracy. So we can make predictions. So we make predictions on the testing set, and we evaluate the performance of our model just as we did in regression. So here, as you can see, it has given us a confusion matrix for how it has performed. So it has correctly identified 74 benign tumors and 44 malignant tumors, with only one instance being incorrectly identified. And we can also see that the highest accuracy achieved is 0.991597. So let's see if we can improve this performance by implementing hyperparameter tuning. So what we do is we define our set of hyperparameters. We create a grid search by giving it the model and the hyperparameters, and then we train our model. We train the grid search. So we train the models and we get the best model. Then we will print the best parameters out. So finished hyperparameter tuning. We have the best model parameters down here, but what we're interested in is the model's performance. As we can see, the highest accuracy attained was 0.96444. Yeah, it's consistent with what we had gotten earlier. So moving on to another model, let's look at the deep learning estimator. A deep learning estimator is a powerful model that is capable of learning complex patterns and relationships between data. So they're well suited for tasks involving large volumes of high dimensional data. Similar to the previous models, we import the model, we create an instance of the H2O deep learning estimator, and then we train it by giving it the class of predictors, the response column, and the training data set. And then we can print information about the model to see how it has performed. As you can see, we have our confusion matrix here with 281 and 100 benign and 165 malignant tumors having been identified correctly, and 4 instances having been identified incorrectly. So for this model, the maximum accuracy attained was 0.99111, which is very good. And we can even see the variable importance. We have concave points underscore mean being the most important variable, followed by radius worst, area underscore SE, texture underscore mean. So in that order. So a deep learning model has multiple hidden layers and uses the ReLU function in its hidden layers and softmax activation function in its output layers for classification. So from the confusion matrix, we have a very high rate of true positive and true negative. This indicates a very strong predictive power. And we have, as we have seen, we also have our variable importances listed for us. Now we can make predictions using the deep learning estimator and evaluate its performance when given the testing set. So as you can see, our maximum accuracy attained is 0.991597. And then we have 74 benign and 44 malignant tumors having been identified correctly, with only 1 instance having been identified incorrectly. So we have very low error rates, and the majority of our predictors are correct, with only one false positives, no false negatives for the class benign. So the model is already performing really well. Let's see if we can be able to improve its performance even further by tuning hyperparameters. So we define our set of hyperparameters. We create a grid search by giving H2O grid search our model and hyperparameters. We also train the models and use cross-validation. So when you add this n false equals 5, we're training using cross-validation. And then we get the best model and we print out the best parameters. So we have our best parameters here, but what we are interested in is the performance. Let's look at the model performance. So as you can see, 279 benign and 168 malignant tumors were identified correctly, and 3 instances were identified incorrectly. We had a maximum accuracy of 0.993333, which is higher than what we had earlier, which was 0.99111. So we've been able to improve the accuracy. Now, after this, we have a challenge here, a classification challenge, where we have a data set that has the characteristics of a species of flower called iris. So we have the data and the corresponding species. What we're required to do is implement a generalized linear model to predict the flower species and then evaluate the performance of the classifier. You can also choose to tune hyperparameters for the model so that you can see if you will be able to improve its performance. Moving on to classification using AutoML, this is similar to regression using AutoML. We import H2O AutoML. We create an instance of the AutoML class. We specify the max runtime in seconds, which I've specified as 600. We specify the stopping metrics. Since now we're dealing with classification, we will use log loss, and we specify a project name, for which here I'll just use classification example. And then we train the model by giving it the class of predictors, the response column, and the training data set. And then we can print out the leaderboard and see which models have performed best. So our AutoML has been able to finish model selection and hyperparameter tuning. And as we can see, there's a column C33, which is bad or unused. So it has been dropped throughout the process. Now we can see that the best performer here is a deep learning model. The best performance were deep learning models. And they're sorted based on their AUC value, the area under the curve value. So the best model has the highest area under the curve model, area under the curve score. So we can get the best model from AutoML, and we can make predictions and print its performance. So as we can see, from the confusion matrix, 73 benign and 43 malignant tumors were identified correctly, and only 3 instances have been misidentified. Our highest accuracy is 0.97479. Yeah. So we have low error rates around classes, with majority of predictions being correct. So only 3 false positives and no false negatives. Moving on to clustering. So here we are interested in grouping elements based on their features. So first of all, we will import our data set using H2O from this link, and we will preview the data set. We will look at how the data set looks like. As we can see, we have, so this is the iris data set. It is data set about flowers and their species, but we have taken out the species column so that we can perform clustering. So first of all, we will scale. After importing our data, we will scale our data. We will use we will use a feature called scale. So scaled clustering data is equal to clustering data.scale. This makes sure that every single variable is given the same importance as the others. So there are different ways of determining the optimal number of clusters. First of all, we have the elbow method. Then we will also look at the dendrogram method. So for the elbow method, we will import H2O k-means estimator, and we will write a function that determines the optimal number of clusters. So to this function, we will also define the maximum clusters we want, let's say 10, and the inertia. So inertia is equal to our function elbow underscore method, and to it we give our scaled data and the maximum number of clusters. Then we can plot this on a graph to see where the elbow point is. So as we can see, our elbow point is at 3. So the optimal number of clusters for this data set is 3. We can also use the dendrogram method. Now the dendrogram method requires importing dendrogram and linkage, which are from scipy.cluster.hierarchy. And then we write this function that plots the dendrogram, and we plot the dendrogram using our scaled data. So this method, it provides a graphical representation of the hierarchical clusters or the hierarchical relationships between the instances. So as we can see, we can say the optimal number of clusters in this case is 3 as well. So moving on to modeling, we will model using the k-means clustering algorithm. First of all, we import it, and then we define an instance of the k-means estimator, and then we train it using the data set, the whole data set. So here's just some information about the k-means model. So you can see here, model summary, we have number of rows being 150, number of clusters being 3, number of categorical columns being 0, number of iterations within cluster being 8, and so on and so forth. So we can predict cluster labels using the k-means clustering algorithm. So we define the predictions being as k-means.predict, and we give it the clustering data, and then k-means underscore clusters will be equal to k-means underscore predictions at predict, and then as data frame. After this, now that we have our clusters, we know where our data points, how our data points have been clustered. So we want to know how well has the model clustered the data. So how well defined are the clusters? From this, we will implement a function to calculate silhouette score for us from scikit-learn. Now, silhouette score is a way of measuring how well defined the clusters are. The higher the score, the better the separation between clusters. The lower the score, the worse the separation between clusters, which means there is overlap between clusters. So what we do is we define the silhouette score using silhouette underscore function, and we give it scaled clustering data as a data frame, and then the clusters that have been obtained, and then we can print the silhouette score. So here we have a silhouette score of 0.46304. This indicates that our clusters are moderately well separated with some overlap. So the clustering algorithm has successfully partitioned the data into clusters, but there is still room for improvement. And now on to the last challenge. So this challenge requires you to make use of a k-means model to perform clustering on the wine dataset. So this is a dataset of wine, and features of wine, for example, the level of alcohol, the level of other components within the wine. So what you do is determine the optimal number of clusters and then perform clustering using a k-means model. After that, you have to shut down your H2O cluster, which we had initialized at the beginning, so we have to shut it down. So after this, you should be able to finish the challenges and gauge how well you have done them. A solution notebook will be provided, and then you should also try the project and see how well you have understood the concept.